Autoencoders, when designed in the right way, can perform principal components analysis. How are these neural networks designed? We'll quickly summarize what we know of autoencoders so far, and then we'll see how we can achieve everything that an autoencoder is supposed to do using a neural network. Autoencoders are the ultimate look within technique. They are an unsupervised ML technique which work on training data with no corresponding labels. Autoencoders are simply neural networks, and the whole purpose of that neural network is to reconstruct the input that it is fed in at the output. This would be trivial if all the neural network had to do was simply copy over the input to the output. However, we place several different constraints or kinds of constraints on neural networks in order to force it to learn the features in the data. In order to understand how constraining the neural network forces the autoencoder to learn new features, let's look at a very trivial autoencoder. This simply has one layer of neurons, and these neurons accept the X input, X1 through Xn, and simply copy this input over to the output. Now, the output Y1 through Yn is exactly equal to the input. This is the trivial autoencoder. I mean, this can be called an autoencoder, but really it does nothing. This neural network trivially learns the input and just spits it out. This is a neural network with exactly one layer. The same layer serves as the input and the output layer. Because autoencoders try to reconstruct the input and the output layer should have the exact same dimensions, and the dimensionality of the input layer is equal to the dimensionality of the input data, which means the output layer should have the same dimensionality as the input data. In this, because the input layer is equal to the output layer, the input layer and the output layer have the same dimensionality, and this is equal to the input data. And this trivial autoencoder simply copies the input to the output. So the output is exactly equal to the input. It's a perfect reconstruction, it's a lossless reconstruction. This trivial autoencoder achieves exactly nothing. There is no change in the dimensionality of the input. The autoencoder hasn't learned anything. We can now move on to constraining this neural network to force the input to be represented with lower dimensionality. So we have the same input and the same dimensions of the output, but this input is then fed to a hidden layer with lower dimensionality, and this hidden layer here is H1 to H3. The output of the hidden layer is then fed to an output layer, and then at the output you receive Y1 through Yn, but the output here will not be exactly equal to the input. The output will not be a faithful reproduction of the input. There will be some error introduced. And this error is due to the fact that we force the input to be represented in lower dimensionality. The dimensionality of the neural network, as defined by the hidden layer, which has just three neurons, is lower than that of the input, which has n dimensions. The trivial autoencoder, we added a middle layer with just three neurons. The choice of three here is kind of arbitrary. You could have chosen any number as long as it's less than the number of inputs. What this hidden layer does is that it forces an n dimensional input to be represented in terms of three neurons or three dimensions, which is why the reconstructed output will not be a perfect match. The input and the output layers of the autoencoder are now separated by this hidden layer, but each of these must have the same dimensionality as the input. In order for the input to be reconstructed as the output, this constraint still remains. They must have the same number of dimensions, they must have the same number of neurons. The objective of the autoencoder is to reconstruct the input to the best of its ability, and this it can do only if the output layer is equal to the dimensionality of the input layer, equal to the dimensions of the input that we feed into this autoencoder. The number of neurons in the hidden layer is less than the number of neurons in the input layer. This is what makes this an undercomplete autoencoder. It cannot reconstruct the input completely. It is undercomplete, and undercomplete autoencoders have this characteristic sandwich like appearance. The output layer is equal to the input layer, the middle layer is smaller. The autoencoder will still try to exactly reconstruct the input at the output. It'll try to perform an exact match, but it's not likely to succeed completely because of our smaller hidden layer, which can learn only a few of the most important features that were fed in at the input. Because of dimensionality reduction, the output will not be the same as the input. You can visualize the example that we saw earlier. We fed in a horse and a bird, and it tries to reconstruct a horse and a bird, but doesn't succeed completely. There is something lacking, there is an error in the output. This error is called a reconstruction error. When we train this autoencoder neural network, we will try and minimize this reconstruction error. This will force the autoencoder to learn the most significant characteristics of the underlying data. It will be forced to look at the latent features. The most important features are the ones that will help the autoencoder mimic the input as closely as possible. Training an autoencoder requires us to set up an objective function or a cost function which defines how far away the output of the neural network is from the input. One possible choice for this cost function is the MSE or the mean square error, which we've been learning about ever since our regression days. This is a design choice that we have. The mean square error, however, is widely used. Another design choice is the activation function that we would use for the hidden layer neurons. Remember, we have many choices of activation functions such as the ReLU, the hyperbolic tangent, and so on. If you recall our discussions on a single neuron, you know that a neuron applies two functions to its inputs, the affine transformation and the activation function. The affine transformation allows it to learn linear relationships between its input and the corresponding output. The activation function is what allows it to learn more complex arbitrary relationships. One possible design choice could be that your hidden layer has no activation function. Its activation is set to none. The activation is simply the identity function. It simply passes the linear transformation out to the output of the neuron. If you set up an autoencoder using these two design choices that we just spoke of, a linear activation or a linear neuron for the hidden layers and the mean square error as our reconstruction loss, our autoencoder will perform principal components analysis. Autoencoders, which have linear neurons in their hidden layers and are trained to minimize the mean square error, will simply perform principal components analysis. And we'll see exactly how this works. In fact, we'll prove that these autoencoders perform the principal components analysis in a demo that's coming up. Let's go back to our undercomplete autoencoder and learn some terminology that will allow us to describe the process that we just spoke of. The central hidden layer is called the coding layer. This hidden layer is what contains a coded or an encoded representation of the input data. The process of converting the input data to its encoded form is called encoding. Input to the coding layer is called encoding, and from the coding layer to the output is called decoding. Representing this data using a reduced dimensionality code force autoencoders to learn what features really matter. Autoencoders, where the hidden layer is made up of linear neurons, that is, the activation function is set to none, and the reconstruction loss is calculated using mean square error, essentially performs principal components analysis.